I'm going to be giving a very brief introduction to machine learning and specifically neural networks in remote sensing and more specifically dealing with ICESat-2 data. So just a little motivational blurb is that, just in general, we are transitioning into a new regime of big data in the geosciences. And a lot of the tasks that could have been done before using more manual approaches, such as classifying different surfaces from satellite data by hand, or running analytical approaches that worked in one region but wouldn't generalize to other regions. These are not going to scale with the amount of data that we have these days. And so basically using the new developments on the tech side with machine learning, and I'm sure you guys have all seen those YouTube videos where like they identify all the cats and the dogs in the video automatically and can segment it. That stuff is super useful for our field, and actually being able to use some of that to get science out of remote sensing data. So that's the kind of motivational blurb. This is a big field, and we are definitely not even gonna scratch the surface today, but I'm just gonna focus on neural networks and specifically using a relatively high level library, Keras, that's easy to work with. But again, there's way more to this, and I'm happy to talk afterwards with people throughout the hack week, well, the remaining days, if they want to find out more. Yeah, so neural networks, I'm going to start just with a bit of the theory, and then we can start running some stuff together. So you can think of neural networks as a series of basically nonlinear transformations that take in some field and apply a series of transformations to approximate some desired output that you want to have based on some training data that you have that already tells you what the output should be. So the idea is, if you have a network like this, you have some input layers, and there's each unit or each neuron is associated with a bias that we call B, and a bunch of weights that basically weigh the input from the previous layer. So that each cell, so for example, if we take A1 here, it takes the output of all the previous units, but each one of them is weighted by some weight that's adjustable. So these are the parameters that we're actually optimizing. And by weighing the inputs, we get a sum input by doing a dot product between all the weights and all the inputs. And then we have a bias. You can think of it as like the activation energy of the neuron in a way. And so we add the bias associated with this cell, and that's again a trainable parameter. And with this input, we can apply a non-linear transformation function, F, and have an output from this cell, then that goes on to the next cell, and we just keep going on like that. So basically the idea is to just do a dot product between the inputs and the weights, add the bias, and then apply a transformation, activation function, which is basically what's written here. So the sum of all the inputs, the bias, and the activation function. So what is the activation function? I'm trying to keep this as short and simple as possible, so we're not going to get too much into the nitty-gritty, but the idea is basically to have these nonlinear transformations, because if you just simply do linear transformations 50 times over, a sum of linear transformations can always be equal to another linear function that does the same thing. But if you have nonlinear functions, you can transform some input to some given output. And so these nonlinear activation functions, there's many functions that people use. There is sigmoid, for example, that's given by this. So Z here is this whole term in the bracket here. We're just going to start calling that Z for to make it shorter. So you can basically do like a sigmoid shape, an exponential. So if I run it, you can see what it looks like. So something like this, where you basically have a very small output with some exponential and then decay, and then kind of going to 1. And you can see that it constrains it between 0 and 1. So that's useful when, for example, we deal with probabilities, and I'll talk about some of that. There's a rectified linear unit, which is just given by the maximum between 0 and the value of z. So if you run that, that looks something like this. And this allows you to basically, well, this is a very popular activation function. So you can think of it like when we adjust these weights and biases, we are basically using an optimizer like gradient descent, where, you know, if you want to just solve some sort of a regression problem with a loss function, you have a way of doing a numerical optimization like gradient descent, where in this landscape of weights and biases, you basically go down towards the minimum. And these activation functions, a lot of the decisions that go into what to use goes into how the training is going to be. So different activation functions have different convergence rates, different behavior. So for example, with these guys, imagine if you're in the flat zone in the negative part here. If you do gradient descent, if you're taking the gradient to find the minimum, you're in the flat area, so you're not going to move at all. So this creates a dead neuron. So then there's newer activation functions people use, like leaky ReLU, that has a slight negative slope, so you avoid dead cells. And again, this is a big discussion that goes beyond the scope of this tutorial, but I'm just giving you a taste of different things. Okay, so that's a bit on the theory side, and I gotta move on with the time here. So we're gonna use Keras in this notebook, which is based on TensorFlow, which is this framework that's very popular for machine learning. And Keras is sort of a higher level library that lets you just call a lot of these different types of layers and whatnot to use them. So if you all go ahead and import or run the first cell, we're going to import Keras. And if you run it, you notice that it says it's using the TensorFlow backend. So there's actually 2 backends you could use with this. We're going to use the TensorFlow backend. And just to take you through a very basic example before getting to the altimetry example, we're just going to use the MNIST data. So this is just a series of images of handwritten digits. So imagine with a pen and paper, you just write 1, 2, 3, 4, different people write it, different handwritings. And we want to be able to just look at a picture and know what digit it actually is. So luckily for us, this is preloaded into Keras as a sample data. So by using the load data function for MNIST, we can just import it. And we have the data itself, which is the images, which is X train, and then the labels that tell you simply what number each image is, and that's Y train. And it also provides us a test data set that we're not going to use in the training, but we can test the data with afterwards. So just to get an idea of what this data looks like, so basically I'm just printing the first 20 elements here, just in a simple for loop. So on the bottom, you can see these are the images. So these are 28 by 28 pixel grayscale images, and we actually have 60,000 of them. And on the top, you see the actual label associated with them. So in order to do this simple classification task, we want to we want to have an output where instead of just telling you what number it is, we want to provide probabilities for a given input. How likely is it to belong to each of these 10 categories? The 10 categories being digits from 0 to 9. So what we're going to do is something called one-hot encoding, where we basically have an array of 10 elements. And for example, if you have the number 3, as I'm showing here, that would just be probability 0 for all the other digits. And then the 3 element, which is the 4th index, since we start from 0, that has a probability of 100% being 3. So that's how we represent 3. If you want to represent 9, it would be all zeros, and then the last element is 1. Probability of 1 that you're in the last category, which is 9. So luckily for us, Keras has a built-in function to automatically convert our data to one-hot encoding. So we simply use the 2 categorical function, and we provide the number of classes, which is 10. So I just went ahead and ran this. Now we're actually gonna start making a neural network. So I realize this might be a little fast, but you have access to this notebook, and introducing neural networks in a 45-minute session is gonna be tricky no matter what. So just do your best, and if you have questions, feel free to ask. So Keras has a very nice option for making sequential models. So we're going to use this sequential class, and we're going to make an instance called model. And this allows you to sequentially define the different layers of your neural network. So basically, we initialize our model as a sequential instance, and we are going to go ahead and define the layers one by one. So first, we're going to add a dense layer. So a dense layer, all it is it basically does the dot product of the inputs and all the weights plus the bias, exactly like what I talked about up here. And importantly, it connects every input from the previous layer to each cell in the outer layer. So basically, all these inputs with the weights go into here, then all go into here. So it's a dense network for between those two layers. So we're going to use a ReLU activation function. So that's the kind of flat line and then slope one line that I talked about. And the input, we're simply going to flatten the images. So instead of 28 by 28, it's just going to be a long array of 28 squared values. So this is, again, this is all just defining the model. We haven't fed in any data yet. So we're just using the shape of our training data. We're going to make, and so originally we had 60,000 images. And notice that we haven't specified that here because we haven't put in the data, but we have specified the dimensions of the data that's going to go in. And we're just going to have 64 units, which is specified by this in the first hidden layer. So if you look at this, that basically means the number of input units is 28 squared because each pixel is a input. And then here we're going to have 64 cells. And then we're going to make a second layer with 32 cells, again using ReLU, and then finally 10 categories. And now we're going to use an activation function called softmax, which basically, well, it's given by this function down here, and it's basically just a normalized exponential function. It restricts it to the output to 0 to 1, and it's normalized. So basically, if you sum up the probabilities at the last layer, it should sum up to 1. And for each of the categories, you basically get a probability of how likely it is that the given input is that particular number. So I'm going to go ahead and run this. And in order to actually fit the model, first we have to compile it. One thing is we have to provide an optimizer. So again, I'm not going to get too much into this, but that's basically what numerical methods are using to find the optimum parameters. So this is like gradient descent, or like Newton's method, whatever. But we're going to use the atom method here, which is a pretty popular method. The loss function basically tells you what it is that you want to optimize. So we basically want our output to be as similar to the training labels as possible. And here we're going to use the categorical cross entropy, which is given by this formula. So basically, Y is the training labels. So for a given category, so if we have M equal to 10 categories, we're going to sum over each of the categories at the end of each iteration, and say we have our actual number is 2. When we get to category 2, the probability of Y being 2 is 100%. So this is 1. And if this guy, oh, I'm missing a negative sign here. I should fix that there. I'll add it right now. So the probability, here we go. The probability of our output being 2, if it's also close to 1, then it's the log of 1 is 0, so our loss function goes to 0, which is what we want. We want to minimize it. If it's not, say we have a very small probability that it's the same number, then log of say 0.001, we're going to get some larger number. And because this is, and it's going to be a negative number, but since this is negative, we're going to get a large positive number. And so this allows us to minimize the loss function and converge our predictions. And we're going to keep track of the accuracy of the neural network. So I'm going to go ahead and compile our model. And we can actually create checkpoints. So we can save the model as we're training it, which is not going to matter as much here because this is going to be a toy example with very short training time. But if you're training something for hours and hours, you want to save the neural network not at the end, but as you go through. So There's something called callbacks, which are super useful. There's many different callback options, such as, you know, if your learning starts to plateau, you could reduce the learning rate in your gradient descent and things like that. Again, not gonna get into it, but we're gonna make a checkpoint. So I'm just gonna make a file called MNIST model, and it's an HDF5 file. And basically by creating this model checkpoint, I'm specifying to only save the best, so only if the loss functions actually reduce at each iteration or at each epoch, then you can go ahead and save it. So I'm gonna run this, and now we can go ahead and train our model. So we can use the model.fit function, and remember that we wanna flatten our images. So the first dimension is the actual number of training images that we have. So this is 60,000. But the second dimension is the flattened array. So the width times the height of the images. And our training labels, which is the second argument of the fit function, is gonna be the one-hot encoded labels. And batch size and epoch. Batch size refers to how many images do you feed into the optimizer at once to basically do one set of optimization for the parameters. So here we're gonna feed in 32 images at a time and go through the optimization, update our parameters, and then do it again. So we keep doing batches of 32 until we go through the whole 60,000 images. And that's only one epoch. And then we're gonna repeat that 5 times because we're giving it 5 epochs. And then we're just gonna give it the callback option as the checkpoint, so it actually saves it. So if I run this, you see that it starts to train our neural network. And this should take about maybe 30 seconds. So you can see the estimated time. It's a little slower now, probably because everyone is running it, I hope at least. So this took about 15 seconds, and there's 5 of them, so 15 times 5. So while this is running, notice that it saved our model into this HDF5 file that is here. And while it's running, I'll go through the next cell, and then we can come back and revisit this. So we can actually also evaluate the performance of our model. So again, with the test data set, we want to go ahead and do the one-hot encoding for the test data set, same thing. And instead of doing the fit, we're going to do the evaluate function. Now we don't need the epochs and the batches and stuff because we're not training, but we're just going to give it the test data set as before and see what happens. So this is basically done, another 9 seconds, and we can go ahead and see with the test data set that it hasn't seen before. So now we're testing the generalizability. How accurate is our model in predicting what a number actually is? So I'm going to go ahead and do the evaluate cell, and the first output here gives you the value of the loss function. So this is literally the output of this loss function here. The second argument is the metrics that we specified when we compiled our model. So this is the accuracy. So we've basically predicted what these numbers are with 95% accuracy, which is pretty impressive given that we just ran this for like 75 seconds, very short amount of time. And you could also save a model afterwards if you want, just using the save option, but we've already saved it. This is just for your own information. And if you have a model saved, you could load the weights. So for people that maybe are stuck, I have the pre-saved model in the repo, and if you uncomment this, you could simply use you still have to compile your model, but instead of training it, you could just load weights from the file, and that basically starts at this step, and you can simply evaluate it. So how are we doing? Well, how are we doing on time, first of all? Okay. So now I'm gonna keep going on this. Is everyone good? All right, cool. I'm getting a thumbs up from Shane. So that was an example of classification. Now we're gonna move on to regression. And now we're gonna do something with ATL03 like data. So because neural networks take a lot of training data, and we don't want to spend half of this tutorial downloading hundreds and hundreds of data scenes, we're just going to make up our own data, kind of like ATL03, and just do a toy example. So what I'm going to do is make the 2,000 line segments. each with width 40 units. You know, you could think of it as meters or whatever you want. And within those, we're going to sample 30 points from that scene. And for those 30 points, we're going to add some noise and basically make a point cloud and then try to regress it to get the line back with the neural network. So I have 2,000 tiles, each with width 40. We're going to sample the 30 points, and we're going to, for each sample coordinate, we're going to repeat this process 3 times. So we have 3 different noise levels. So we just initialize our random generator. So we have a set of coordinates and we have a set of parameters. So the parameters are basically the slope and the intercepts. And these are the things that we want to recover with our neural network. And the coordinates are simply just the coordinates of the points. That's going to be our training data. So I'm going to give the neural network the X and Y coordinates and train it based on the intercept and slope that we already know because we created the data. And then it should be able to estimate the line parameters for a new set of coordinates, new data. So I'm just going to run this cell. All this does basically will be created a uniformly random set of slopes and intercepts between the range of -4 and 4. And notice both for the coordinates and the parameters, there's dimension 2 at the end, because for the coordinates, we have both X and Y, and for parameters, we have slope and intercept. So we're going to make a line by adding the, this is basically the slope plus all the X values, which is, this is the width times the slope. And then we're going to add some Gaussian noise. So just using the NumPy normal distribution random number generator with mean 0, and we're going to use a standard deviation of 5. And we're going to basically populate this line. And then we're going to start sampling points, so 30 points, and then do it 3 times and create these coordinates with the noise that we're going to deal with later. So I already went and ran this. So now I'm going to separate it into 10% of the data is going to be for testing. That's not going to be seen by the neural network during our training, and the rest is going to be for training. So again, I'm going to extract, I'm going to basically make random indices using the randints option for basically 90% of, or 10% of the total number of data points. And I'm going to pass those to the chords and the parameters as our test arrays, and the rest is going to go. So all this line does is to just get the rest of the indices, so the complementary set, and pass it as the training labels. And if we do this right, then the intersection between these 2 indices should be 0. There should be no data point that's both in the test set and the training set. So that this last line just confirms that we did everything right. And sure enough, it's empty, so that's good. So if this is confusing, this is just a setup for the problem. It's not part of machine learning, so don't worry about it too much. But if I plot it, basically looks something like this. So I'm just plotting the first 4. Remember, we have 2,000 of these. And this is kind of like our a very toy simulation example of ATLO3 data. So we have these lines that we created, and then we added these data points around it with these kind of vertical profiles, kind of like ATLO3, with different noise levels. And we're going to try to do this regression problem with a neural network. So here, if there's time, I'm going to ask people to go into a breakout session, maybe for just 5-6 minutes, since we're running a little short on time, to see if we can create a similar neural network, kind of like we did up here, but to do this regression problem. And to give you a hint, you could basically do a very similar thing as we did before, but for the last layer, you don't want to use a softmax activation anymore, because that gives you probabilities between 0s and 1s to classify things. But we want to actually preserve the output of the last layer, so you can use a linear activation. So if you just set activation equal to linear, there's no transformation at the very end, and that should be able to give it to you. So just give it a try, and then we're going to go through it together. So don't worry if you can't get it. But Jane, I don't know if you are ready to break out into the sessions, and we can resume from there. Yes, no? Or if not, I could just keep going through the notebook. I don't know how we're doing on time. Got another 5 minutes. Okay, I'm not hearing anything, and I'm a little worried about time, so I can hand it to Shane. So I'm just gonna keep going through this. We can just skip the breakout. Okay, so, but I'll just wait maybe 30 seconds for people to catch up, since this was kind of a breaking point, if they have any questions. So is everything good so far? Maybe Shane, can you give me a thumbs up or down? Everything is good? All right. Okay, so yeah, I'm just gonna go ahead and continue then. Okay, so I was gonna fill my solution here. I'll just do it now. So what we're gonna do, well, for the sake of time, I saved it here. I'm just gonna copy paste it. A little cheating here. There we go. Here. All right. So what I'm gonna do is define a new model, again, using the sequential instance. And we're gonna start adding dense layers as before, using, again, we can use ReLU activation functions. And in your spare time, you could experiment with changing these activation functions and see what happens. Try leaky ReLU or the other ones, or sigmoid, see what happens. Well, one nice thing about ReLU, before I forget, is that it's not constrained in its range. So sigmoid is between 0 and 1, for example. ReLU could go as in any range, which is good for problems that don't inherently have a constraint. But anyways, feel free to experiment with those. So I'm not going to spend too much time on these first couple of years. This is the same as before. Our input is going to be the shapes. So again, this is just like before. We have our array with the training data. The first element, so shape 0, would be the total number of data points. That's the number of tiles, 2000. And then the last two are the dimensions of each instance. So we're going to go 128 neurons in the first layer, and then double that, and then do another 258. So that's 3 hidden layers. And again, feel free to experiment with those. You could add more layers, less layers, change these numbers, see what happens. And lastly, our last layer, we just want 2 outputs in our regression. One of them is going to be the intercepts, and the other one is going to be the slope of the line. And the activation function is linear here, again, because we just want to preserve the output, whatever the slope and the intercept are. We're not, mapping it onto some probability space or something else. Since we're doing a regression problem, for the loss function, it just shows the mean squared error. So that's the thing we're trying to minimize. Again, using the atom optimizer, and we're going to keep track of the accuracy. So if I run this, what's going on here? Oh yeah, let me just change the name. I think it's because I didn't change. So X should be actually chords here. There we go. Cool. So I also did the model.summary option here, which shows you what the neural network looks like. So we have these dense layers, and you even get the output shape for each layer, 128, 256, 256, and 2, as we specified, and even the number of trainable parameters. And what's cool, you could also even plot the architecture of the models. So if I run this, you basically, this is super useful when you start to get more and more complicated neural networks with all sorts of disconnected arrows and parallel layers and whatnot. But it gives you the dimensions and just what each network is. So again, I'm going to go ahead and create a checkpoint callback option. This time we're going to call the model regression model .htf5, and again, monitor the loss, only save the best, and we're going to train the model. This is the same as before. This is the number of training labels. This is the input dimensions. We're flattening it again, and the training data, and 30 epochs, 30 batches, and with the checkpoint. So this should be faster to train. Yeah, each epoch takes about 2 seconds, but we're doing 30 epochs. So let's just give it a second and see what happens. And while that's running, we're going to test this both on the test data set and on the training data set, just to make a point about the importance of the test data set. So notice that in the first couple of steps, every time the loss is improving, it gives you what the loss value is, and the accuracy keeps improving. And at some point, whenever the loss doesn't improve, it does not save it to the model because we have set it to only save the best case. There we go. So this is trained. And once again, we're going to use the evaluate option. And we give it the dimensions as before and the test data set. And we set variables to 1. So we see the information. And so we're going to do this. And again, the first element is the value of the loss function. So this is the mean squared error. And this is the accuracy. So it's okay, 67% accuracy. But again, this is the toy example. This is not something you actually do in real life. And we just ran it for a little bit. But if you run it on the training data that we actually use to train a network, so let's do this, we get an accuracy of 91%, which kind of tells you that you're overfitting this. You're just basically having it memorize the training data the way it is. Just wanted to make a point that that's why you always want to have a test data that's not seen during training and test your network on that, because you get very different answers. And in reality, there's ways to avoid overfitting when you do this, you know, for actual research purposes. You want to also have a validation data set in addition to the test data set. And you could feed the validation data set to the fit model. And what that does is that every iteration, every epoch, it sets aside randomly, say 10% of your data as validation, and tests the new optimized parameters on the validation set and see how that's changing. So if you plot the history, at some point you see the training accuracy keeps going up, or, you know, the loss function keeps going down, but the validation at some point starts to go back up. And that's when you want to actually stop the training because you're overfitting. And there's callbacks for that to stop when you start to overfit. But all of that is beyond the scope of the course. This is a very rough intro. So I'm going to leave it at that. I think, look at that, 45 exactly, cool. Yeah, so I'm going to pass it over to Shane. And yeah, here, I'm going to stop sharing.
All right, thanks, Yara. That was great. You can go ahead and share my screen in just 1 second. Let's see here. All right. Can everyone see my Jupyter Hub instance? Getting a thumbs up?
Yeah, you're good.
All right. So let's see here. I'm going to go ahead and click out of Slack so that we don't get pinged with notifications for that. So as Jessica mentioned, my name is Shane Grigsby. I am actually on a split appointment. I have about 20% time at the University of Colorado and then 80% time at the Department of Geophysics over at Colorado School of Mines. I'm going to be talking about inference using Bayesian networks. I think this is the last tutorial, so I'll try and go through this a little bit slowly, because I know that people are starting to get a little bit fried from all the material. Before I jump into this, I'll just kind of mention that this tutorial is on machine learning. Machine learning is a really, really big space, and so we've just kind of highlighted two sort of interesting cases. One resource I use a lot for machine learning for my own work is scikit-learn. If you go to their user guide, you'll see that they have quite a lot of different types of machine learning. So everything that Yara talked is sort of this 1.17, so one of 17 options out of specifically supervised learning, and there's also unsupervised learning and a bunch of other options. So I like using them, the scikit-learn people, because they have really good documentation. Some of the stuff that might be useful for people's projects are Gaussian processes for interpolation. This is quite long in terms of what the documentation is. Clustering, I'll just highlight that there's these two methods here, dbScan and optics, that are density-based. And so you'll note that when you actually run these sorts of clustering algorithms, they have an option for not classifying all of the points. So here where my mouse is going over, you can see that some of these points have been classified as black dots or noise. So it's a good way to try and do some sort of classification when you don't actually want every single data point assigned to a class. And if you drill down into that, you can see that there's dbScan and optics, and these have links inside for actually looking at demos for how to use this. So I guess with that, I'm going to switch back to what I'm actually talking about, which is inference using Bayesian networks. Bayesian networks are called sort of belief networks, and they're a type of way of sort of specifying causal relationships between different variables. So this is an example I like a lot, which is basically you could be looking at, you walk outside and you see that your grass is wet, and you'd like to know why your grass is wet. And there's kind of two different causal chains that you could have that cause that. The sprinkler could be on, or it could have rained. And then you can start to formulate a belief about which one of these variables was actually causing that cause based off of whether or not it's cloudy out. So in this example, we have cloudy is actually conditionally dependent on sprinkler and on rain. So if it's cloudy, it's say 80% likelihood that there's rain and maybe 20% likelihood that there's not. The way that this particular example has been formulated is that there's actually a causal dependence on the sprinkler. So the person who sort of set this up imagined that someone is actually turning the sprinkler on. So if your neighbor is going out and if they're actually turning the water on, they're probably more likely to do that if it is sunny out, and less likely to do that if it's cloudy out. But you could make this sort of graph however you want, depending upon what your assumptions are. So if you know that your neighbor actually has it on a timer and doesn't actually turn the water on by hand, this edge of this graph might actually not be connected. And so this might be sort of causally independent. So there's a lot of flexibility in terms of how you set this up, in terms of whether or not what the assumptions are that are in your model, where you can have this connected or not connected. But the punchline to this is that, assuming that you actually have someone who's turning this on, if you go outside and the grass is wet, you can form a belief based on how likely it is from rain, based off of whether or not it's cloudy. Because if it's cloudy, it's less likely that the sprinkler was turned on and more likely that it rained. And so you have this conditional likelihood that you're basically calculating. So I think that this specific example is definitely from someone in Europe, because they're using commas instead of points for the bit. There's a link that goes to this blog where they talk about some of the theory and a little bit more background. But basically what Bayesian networks are is that they are directed acyclic graphs. So if you remember, that was actually part of, I think that was part of the theoretical background that we were talking about with Git. That's another instance where you have sort of this directed graph. But they have this property, which I think is called the local Markov property. And that basically states that you've got sort of independence, causal independence, depending upon how you formulate this. So again, if you were to remove this line, if you were to say that your neighbor had their sprinklers on a timer, then cloudy doesn't tell you anything about whether or not the sprinkler was on, because it is not a child anymore. It is not connected to a parent node. So the specific example that I'm going to go through to kind of make this, to show this work, is actually an example from epidemiology. And so if you go ahead and if you run the first couple of lines, you'll see that there's this fictitious biological model where you have sort of a healthy gene and unhealthy gene, and that gene impacts how likely it is that your blood pressure is higher or lower. So if you have this unhealthy gene, your blood pressure is going to be sort of mean of 60 with a standard deviation of 10. And if you don't have this unhealthy gene, then you're going to have this mean of, say, 50 with the same sort of standard deviation. And so basically what this sort of, the way that this is represented graphically is that G1 is this parent, and that this X1 variable is what their blood pressure is. So they should actually have a blood pressure that is reflective of whether or not they have this gene. And then they have some probability, some high probability, but not some absolute not some, certainty in terms of how likely they are to pass on to their kids. So if they have the gene, they have maybe a 90% chance of passing it on to their kids, but they still have a 10% chance of not passing it on to their kids. So you can kind of see that you could have an instance where you could have a parent that has this unhealthy gene. They could actually end up with 2 different kids, and one of those kids might have this, this unhealthy gene, the other one might have the healthy gene, or both might have it. And then each one of these kids, so this is the parent here, G1, this is kid 1 and kid 2, and then each one of the kids has a blood pressure. So there's this latent variable, which is the gene that is reflected in, that is expressed in this observable variable. So this is basically a quick specking out of what is kind of written here in numbers. And I'm going to go to this next line just to basically show what we have. I've defined a model, and then once I've defined the model, then I've actually been able to go ahead and plot it. And this is actually the same as this. It's just graphically displayed a little bit, because if you look at the arrows, this arrow is going up, it's not going down. So you could put this X kind of anywhere, you could put it next to it. And so that's what you kind of see here, is that you've got G1, which is the parent, this is their blood pressure, and then that's going to G2 and G3, which are their kids, and then their kids' blood pressures. And we've gone ahead and we've basically specified up here each one of the kids. So left child, right child, we've given them this Bernoulli variable, which is basically linked up to this sort of, likelihood of having this or not having it. And then we've also been able to put in sort of this normal distribution. So we have a couple of different distributions here. We have a distribution that is a continuous variable. We also have a binary variable. And what we're really doing here is we're actually doing probabilistic programming, where we're able to actually specify sort of different distributions. Some of them might be, multinomial, some of them might be binary, and some of them might be sort of continuous. So I guess the first sort of question that here is, like, let's say that what is the probability that G1 is unhealthy given that X2 is 50? So in words, it's what's the probability that the parent, G1, has the hereditary disease given that one of their children, X2, has a blood pressure of 50. And so this next cell is going to do exactly the same thing as this first cell did. There's only one difference. And the only difference is that I've basically gone through, and earlier I had sort of specified all of these distributions, but I've added a flag to X2 where I've said, rather than just being sort of a mean of whatever this rate is in terms of being 50 or 60 with a standard deviation, I've said I've actually observed this variable. So actually know what this variable is. And so what we're going to be able to do is we're actually going to be able to solve for what these probabilities are. And the way that we're going to do this is that we're going to use Monte Carlo Markov sampling. So we're going to do MCMC. And so basically what this is that if you run this cell, it's going to take a few minutes to basically go through, and it's going to do stochastic draws. So it's going to draw from, this variable X3. It's going to do the mean and the standard deviation of these draws. It's going to draw from these other, distributions. There's a couple of options here. So the first one is basically the number of draws to do. As you bump this number up higher, you get more accurate information. This tune is basically saying how many steps to do. So you have some convergence on the MCMC sampling. And so you can say, okay, I want you to do the first 2,000 just as tuning steps, and I want you to throw those away. I usually actually don't use this tune variable, because normally what I'll do is I'll just take this variable in terms of the number of draws and make it way bigger. So I'll run this for 100,000 or 500,000. And so then the number of tuning steps are sort of lost in the noise, because the first, couple thousand are basically integrated in. As it's doing this, you can see that it's sort of split up 4 different jobs. It's doing sampling for the G1, G2, and G3 variables. And it's also doing sampling for X3 and X1. What it's not doing is it's not sampling X2. And it's not sampling X2 because we've already gone ahead and say, hey, we've observed that variable and we know what it is. I didn't do a whole lot of work here in terms of actually having to specify a lot of this. PyMC3 kind of decided what the appropriate samplers were for us already. So you can see it's using this Metropolis Hastings sampler, and then for the continuous variables, it's using this no U-turn sampler. Once this finishes, it'll take a second for it to kind of finish up. We're going to get what's called a trace, which is basically it's basically the samples. It's basically what was drawn, and you can look at the distributions of the sampling in order to actually answer some of the questions that we have. So it'll take a second for this trace plot to go ahead. So just a reminder, the original question is, what's the probability that the parent has a disease given this blood pressure from the kids? So you'll see that basically you can see the distribution of the different variables. So G1 is the parent. I think that 0 is unhealthy, 1 is healthy. I think I might have gotten that mixed up. G2 is sort of this, you know, the variable for the child. And then you can basically look to see that you've got this sort of summary. So these variables here, this is X1 is the distribution of blood pressures for that child, and then or for that parent rather. So X1 refers to parent. So this is the range of possible blood pressures that we got from sampling. And X3 would be their sibling. So they're you know, not their parent, but their other child. We're not seeing X2 because we said that we know that X2 is set at 50. And then these are the latent variables that have come in terms of the, you know, the amount of times that the latent variable was 1 or 0, with 1 and 0 representing disease or not disease. So I had gone ahead, and this notebook will be different every time that you run it. So originally I'd had this next thing just in text, but I realized that if you actually do run this, that this will change. So basically what happens is that this says that, you know, 90.22% of the G1 samples are healthy. So, you know, there's 7.98% are unhealthy. And we can summarize this information. So there's this nice little summary option, and this will basically print out sort of higher level statistics with error bounds in terms of what each of these variables are. So you can see that there's some confidence bounds, there's a standard deviation, there's a mean. There's also these bits over here in terms of the MC sampler error. And this cell here will basically take information out of that and then print us out something that will hopefully match with what I had earlier said. So let's see here. So, okay, so this is actually a little bit interesting. And this is maybe a good way to go about for a bit of a digression, but there is an analytic answer to this question. I don't usually use the analytic solution because it's kind of a hassle to compute, and also just because I would tend to, especially if I was running this on a machine that had like a GPU, you can run these samplings on the graphics card, so it can get really cheap to run really large numbers. Because we're doing this on sort of these instances, we've tuned it so that the samples are a little bit lower. But this analytic answer is 0.105, so 10.5% basically is the percentage, you know, is the likelihood. So I guess since we're talking in Bayesian sense, we'd say likelihood. If you were a frequentist, you'd say that's the percentage of the population that is unhealthy. But the analytic solution, you know, if you go back to this blog post that I referenced, you're doing this process called marginalization. So for the variables with the sprinkler and the clouds, this is the analytic solution to do this. It's this really big, you're going to calculate sort of all the different probabilities given all the different variables. You're going to sum across it. And this becomes really, really unwieldy to do once you get moderately complicated graphs. So very quickly, even though there is an analytic solution, sometimes this marginalization process is really difficult to do, and it's just easier to sample. So that's kind of what we've tried to do here, is that we've tried to sample. And when it gives you this error estimate, it's going to give you an error estimate based off of statistics that it's estimating. So what I've done here is I've said the MC, the analytic answer is this. This is what the estimate is that we got, this 0.9, and this is the error bound. But that error bound has its own standard deviation. So I think that we're still within error bounds. If you take the mean error and if you look at the standard deviation of the errors, then you could add those on. You could see that, you know, sort of that confidence interval, we're sort of on the edge of it. But you can make this number smaller by increasing the number of samples. There are cases where if the samples are too low, you might actually have cases where you're not quite getting the answer. But if we were to go back up here and if we were to just, I don't know, maybe the way to do this is just to double it. And then we'll have the number of tuning steps. This will go through in a bit and we'll see that we have a different answer. In a second. So one of the nice things though is that, you know, this is generally pretty good in terms of telling you whether or not you're within your error bounds. I trust this, especially when I'm using large samples. After that finishes computing, we'll go ahead and we'll run this again with an order of magnitude less. So right now we're running 20,000 samples. This cell here will run 2,000 samples, and you'll kind of see that you'll get different answers. Hopefully the answer above from the 20,000 will both be closer to the analytic solution in terms of being sort of more precise and also have sort of tighter error bounds, whereas this solution should, you know, ideally we'd like to have something that's still within error bounds, but those bounds to be larger. So we'll see if that actually happens. We'll just take a second for this to finish running. While that's going on, I'll maybe highlight a couple of different things, which is that this observed flag here, I've set this to just be a straight value to be 50. But you know, here we had a distribution, and if you wanted to actually, you could put in an array for this or a list. So you could say, hey, I observed you know, these values. So maybe you actually have something that is not a well-behaved distribution. Maybe it's not Gaussian. You know, maybe you have something that's, you know, bimodal or something. And so you could actually put in the array that represents what those different values were. So you can actually take this and put data in. The other thing, which I think I was going to show later on, but I'll kind of just talk about now as we're waiting for this to run, is that there's a method that will actually take these samples, which is really what you're getting, these summary statistics, and you can convert that to a data frame. So there is a way to kind of, you know, take this stuff and use it with some of the tools that we've been using in terms of actually having a value that is having this data in a format that's sort of H5 files. And I'm guessing that for people who have sort of been running along, some of you, when you ran this first step with the 10,000 originally, I'm guessing actually, you know, did get different answers than what I got, just because this is actually stochastic in terms of what you're getting. If you look at these other plots, which I guess I'll talk about just because we're happening, this will also show you sort of the specific instances in which it chose 0 and the specific instances in which it chose 1. And what's nice about that is it lets you tell you if you maybe haven't reached convergence, because you might have something where there's sort of, you know, if this is changing, if it doesn't look like noise, if you have sort of a higher density of selecting, you know, 1 at 2,000 draws versus at 6,000 draws, that's kind of a hint to you that the sampler hasn't actually approached the correct value. So this looks like this is about done. Hopefully we'll get, you know, it usually takes a second after it finishes sampling to kind of, you know, return and also print out any errors in terms of convergence warnings. But let's see here. Sorry, 1 second. Okay, there we go. So yeah, so it's giving us a warning here that the number of effective samples is smaller than 10% for some parameters. And that can happen because depending upon which direction you're going, you know, since we're fixing this variable of what the, we're asking what the likelihood of the parent was to have the blood pressure, but we're fixing the the child blood pressure, which means that it's going to look at cases for the parents where that latent variable is. And it's going to look at the draws and then try and match. And what it's saying is that there's maybe some parameters that have less than 10% of the cases that were sampled. Most of those issues you're able to basically get around. Okay, so we reran this, so we can already see that just in terms of rerunning the trace, we've already gotten a number that's way closer. So the analytic answer is 10.5. I think last time we had gotten something that was like 9.7. So doubling the number of samples already gave us a better answer. And if you look at these values, my guess is that this error mean is going to go down as well. So this is 0.0069. And then my guess is that when it summarizes, it'll actually be even lower than that in a second. We'll see if that's correct. So there are sort of 20,000 samples with several different variables. So it takes it a second to kind of do that. So yeah, you can see that we dropped, we got a tighter error bound doing that. We also got sort of less of a standard deviation. And so now when I print out this cell, it's going to basically say in a second, so we should get a return from this in a second, which should say, okay, so the analytic answer is 0.10535. The estimate is fairly close to that. These are the error bounds. So basically what the MCMC sampler is saying is that we think that your answer is in between 10.1% and 11.1%. And the analytic solution is 10.5. So maybe a little bit useful to have that actually happen on a live demo. I was going to say that there are cases where if you set these low enough, you can exceed those bounds. This should not take as long to run just because this is literally a factor of 10 less. So if we go ahead and if we do the same thing with say like 2,000, what we'll see is a larger bin in terms of likely values. And my guess is that we'll probably also not have as precise of an answer. So this is running faster because we're doing 10 times less than earlier. It'll still kind of take a second for it to go. It's going to yell at us. It gave us an additional warning flag here in terms of saying that there was a probability that didn't match the probability that it expected. So that's kind of a hint that these values are maybe not quite as close. We got kind of lucky. We could rerun this 10 times. We'd be all over the place. We got actually not super far from the answer, 10.7. That's still not as good as our original answer, which was sort of 10.6. But if you look at the error bounds, you can kind of already see that these values here are sort of an order of magnitude higher. So up here, that value is 0.005. I think that down here, it's 0.01. So that's way larger. And the bounds on this are not nearly as tight because of that. So the second question I had put, this first one was asking the likelihood of the latent variable, which is a binary value, but we can ask other interesting questions. So this is saying what's the likelihood that px3 equals 50 given px2 equals 50. So in English and words, what's the conditional probability that child 2, x3, has blood pressure equal to 50, given that their sibling has normal blood pressure of 50? And really the reason to kind of do this, so I think I had set this one maybe as like a little bit higher, is just that earlier we were asking what the likelihood of, see here if we scroll all the way up while that's happening, these variables G1, G2, G3 are all binary. These variables X2, X3, and X1 are all continuous. So earlier we were saying what's the likelihood that G1 equals 0 or G1 equals 1, what's the likelihood of G1 being true or false basically. And so we only had two options, but now we're looking at these X variables and these are continuous variables, which means that the way that you kind of ask the questions is a little bit different because we're asking what the likelihood of the blood pressure being 50, but the blood pressure could be 50.02 or 50, 3, there's a continuous range. There's not just a yes, no answer. So I thought that that was maybe useful to kind of look at really quickly to see sort of, how we would interpret that. So this is kind of running. I guess I'll kind of talk through this, next. It's not quite as obvious as how to answer this. So you could look at sort of taking the discrete bin to say, what's the, you could say, sum up all the values between 50 and 51, and then look at that as a ratio to the rest of the values, and that would give you some approximation of how likely that case was. And that kind of works for blood pressure because it goes to a nice natural step size, or you could say integer values, but it's not always obvious what the window is. So normally we'd like to kind of do something a little bit different. The library that we're using has also changed just a little bit. So when I first started using PyMC3, these graphs here, these are kernel density functions. It's basically gone through, there was a histogram of different values where it's gone through, and it's basically said, we picked, 41.2 here, we picked 50 here, we picked whatever. So these are all individual discrete values. You can see on the right-hand side, these are the values that's been drawn as the MCMC sampler was going through. And it could have just shown us a histogram, but what's done is it's basically convolved a kernel density function over. And so what you're seeing is the kernel density function, and you can see that there's a couple different lines. And so what it did was that there was that message, I think, earlier about, multi-process sampling 4 chains and 4 jobs. And so each one of these dashed lines is sort of a different job. So you can kind of see what the spread is between the different MCMC chains. But these are all discrete values, and then it's gone ahead and it's dumped these in, and it's kind of done a smooth function over those values. And so earlier versions of PyMC would actually show an axis that would go from 0 to 1. So you could kind of read off of the left-hand side what the likelihood was for each one of those. But just because some time has passed, they've updated their plotting library, so that's no longer exactly how that's done. I might have been a little bit aggressive on the number of samples. So we'll let this continue to go. But I guess to kind of skip to the punchline while that's going, we'll plot the traces and the summary values, but it's not going to necessarily tell you what the value is directly at 50. So the way that I normally solve that problem is it'll actually do exactly what they're doing, which is that I'll bring in this sort of kernel density estimate in order to do that. So down here, a couple lines, you can see that I'm importing from scipy.stats KDE, which is kernel density estimate. And what that lets you do is it lets you basically dump all the data. So this is my trace of X2. This is, the my trace is sort of a pandas-like data frame. And so we're saying, give us the variable named X2, and then convolve a Gaussian kernel density estimate over it. And what it returns is it returns this thing which I'm calling my PDF, and my PDF is a function. So you can put any value of blood pressure, 50, 50.01, 60, doesn't matter what it is, and it will give you what the density estimate is for that value, so that you're not actually having to go through the step of sort of doing discrete, sums to actually get your answer. So let's see here. This is still going on. I guess I'll pause for a second and I'll ask if there are any questions that I can address while this is finishing. Yara, I don't know if you want to take a look on Slack. I closed Slack so that I wouldn't have pings going on, but if there's anything that anyone wants. Nope, okay. So that works. Again, kind of as above, you can see that the sampling has changed a little bit. So we're still sampling G1, G2, and G3. Earlier, for the other exercise, we were sampling X1 and X3. Since we're asking a question about X2, we switched, so we switched the observed from X2 to X3, and so we're not getting that. I think I'll probably skip after this finishes this very last section in terms of this, because I think this was basically just to show that you could use data arrays or list of data when you're doing observed. And it kind of, you can start to ask different types of questions. But I will say that one of the nice things is that you can kind of see in some of the solutions that we were looking to earlier on these plots, these are not really Gaussian. So the functions or the distributions, you can ask questions from non-Gaussian distributions. This might be a combination of Gaussians, but it's not really clear that this is just two Gaussians that are split together. It doesn't really look bimodal to me. And part of that's because the weighting factors are kind of these weird combinations of sort of, X percentage of this and X percentage of that. So you can have very, very, very complicated functions that you can ask questions of that are very specifically not Gaussian. So I think this is probably pretty close to finishing. Let's see here. Yeah, it looks like we're at 100%. It's just collating the data. So it'll take, just a few more moments for it to basically take all the sampling chains and kind of smush them together. All right, so that finished. And so like I said, this is kind of a naive way to do it in terms of looking at sort of discrete bounds. So you could say, hey, what's the sum of things that are that are less than 51 and greater than 50? And you could get something that's close-ish. But really what you want to be doing is you want to be looking at doing it through the kernel density method. So I'll just execute all these kind of simultaneously, and then you'll get, we'll go ahead and we'll have some answers that we can kind of look at in a second to interpret. But generally, my experience of MCMC sampling has been that if you do run into issues, the naive way to kind of get a better answer is just to basically bump up the iterations, because you do actually have this convergence that happens if you run it long enough. And especially if you have anything either where you're able to let it run overnight, or if you're able to sort of run it on a GPU, you can get a pretty good answer. So yeah, so basically this is what I was saying earlier, is that you can take this trace, you can dump it to a data frame. You can see that what you're really getting is you're getting this sort of histogram. We can plot directly from the data frame what the sort of kernel density estimate is, and you can kind of see that we're getting you could almost sort of read off blood pressure of 50 and try and figure out what the density value, which is the same as the likelihood. And then the way that I would normally try and pull this in is I would basically just do this step, but I would sort of make it as a function where I bring in a kernel density estimator. And then from there, you can ask a direct question in terms of what is the estimate. And the nice thing about this is that since you're getting an estimate exactly at that point, you can then sort of take that MCMC error and then use that to apply your error bounds. So again, you kind of have these weird nested errors. You have the mean of your error, and then you have the standard deviation of those errors. So it's kind of like you've got this error bound, this confidence interval, and then the edges of that confidence interval have their own little confidence intervals on top of them. So it's a little bit strange, but basically it's saying that we think that there's this much error that is available. So I think that's kind of all that I really want to say about that. The notebook is posted. People are welcome to kind of download it, mess around with it, change the number of samples or change kind of the questions that you're answering. And I think that what I guess I can do is I can post some of these links afterwards. I guess just for the last few moments, if you do go to the PyMC3 site, they have quite a different number of examples of different types of sort of statistical models that you can use. I don't think that they had anything specifically on Bayesian belief nets, which is partly why I wanted to kind of showcase that. And they have a section on getting started. The other resource, I guess, that I had is that there's this book here, Probabilistic Programming and Bayesian Methods for Hackers. And Fernando had mentioned that there's actually ways where you can write a full textbook in the IPython notebook, which is exactly what they've done. So this is, you can buy this book in paper, in print copy, but you can go and you can look at the Git repo. If you click on something, if you click on, say, chapter 3 MCMC, that'll take you to the repo. And if you click on this read online here, I think it'll basically take one of these chapters and render it for you. And this is basically what you would get if you were to buy the book, is that you have sort of this long sort of digression of likelihoods and priors and how they do things like monitor for convergence and deal with traces. So those are some additional resources. I'll go ahead and I'll either copy paste those links into the Slack channel or just update the README. And I think with that, yeah, I'll go ahead and I'll turn it back over to the other admins.